WIMP searches in gamma rays. So you have already had a lot of introduction material to this specific lecture. I won't actually refer directly to the specific lecture that you had about with which we have links, because basically all of them can be cited here. Please do not hesitate to interrupt me. It's a bit difficult. This is the first really lecture that I gave virtually. So I will try to have a look at the participant list if there are hands raised. And also Miguel perhaps can help me in that. But really, just let's try to keep it as interactive as possible. So feel free to ask questions during the presentation. And I will also stop a couple of times to be sure everyone is on the same page. So then let's start. You can see here my mail as well. Also, if you then after the lecture you have questions, again, don't hesitate to write me. And I will be on Gather Town today, starting from 3:30. I will have a break at 4. I have this quick Skype chat that I have to attend, but I will go back as soon as possible around 4:30. Okay, let's start then. So this is the outline of the talk. I will briefly recap what are WIMPs, what we actually meant with them, and how we can make the connection with the early universe by using actually searches for them today. And I focus then on indirect detection, and especially I want to orientate the talk around spectral features and spatial signatures and what really defines features that are prominently for WIMPs and not for other signals. In this respect, I will present 3 examples of searches that you can make, exploiting some of those characteristics of and properties of the signal. So first, a search in the diffuse gamma ray backgrounds, then searches for line signals, and finally towards specific targets like sub-Eos and dwarf galaxies. I will then go on the TV scale, because there may be actually interesting effects that arise, like Sommerfeld enhancement and Mose formation, which also lead to the importance of having a full formalism that takes into account the velocity dependence of the cross-section and therefore of the astrophysical geometrical factor that describe the signal. And I will finish with just a brief mention on decay WIMPs, because they are also there and searches are performed, and a final comment on how we can switch from a feature-based paradigm for the search to a model-based paradigm. And I have bonus slides if I will be on time and we have more to discuss. Anyhow, let's jump into the topic. So weakly interacting massive particles, you should have received now all the basics on about WIMPs and what we meant with them, but let me just recap it. So you have, you know that the parameter space for that matter is really broad, either in mass and interaction of the cross-section for the interaction of those particles with standard model particles. So this is just a zoom in on a part of the parameter space, because it can be actually much broader. And in this respect, WIMPs are like a sweet spot for interaction cross-section, which are weak but not too weak to actually be targeted with direct detection experiments, and the mass is around the GeV to TeV scale. So the broad range in mass for WIMPs runs from about 2 GeV up to the unitarity bound that is about 100 or a few hundreds of TeV. They have a weak interaction cross-section or even sub-weak with couplings to standard model particles, and typically they are produced through what is called the freeze-out mechanism in the early universe, and I think Laura already explained you how that works. On top of standard WIMP, interesting candidates which are kind of related to them are this called super WIMPs, or extremely weakly interacting massive particles, or FIMP. like axinos, which are the superpartners of axions in SUSY models, or gravitinos, again, fermionic partners of the graviton. And if you allow for R-parity violation models, that you can have that the axino and gravitinos, which are the lightest stable particles in their models, can then decay. So those are actually good candidates for decaying the WIMPs, and they can be produced either thermally or non-thermally through the freezing mechanism in the early universe. And contrary to WIMPs, which are mostly basically candidates for cold dark matter, then depending on the parameter space, our axino and gravitinos can be either hot or warm or cold dark matter. So going back then to WIMPs, so if we stick to the weak scale candidates, then we have actually broad categories of models, which comes within specific theoretical scenarios. So here is just a list, which can give you an idea of the zoology of what are the models that typically are discussed. So the most discussed candidate in the literature, I think, is really the lightest neutralino, which is a combination of the superpartners of the gauge bosons and the X particles in supersymmetric models. And a lot of works have been done studying the phenomenology of neutralino particles with respect to different types of searches. Then you have model where you extend the X sector, where you can add another doublet that produce additional charged and neutral X bosons, and one of them can actually be a good dark matter candidate. And those are models that are called 2X doublet models. And the simple extension in this context is the inner doublet model that maybe some of you have heard of. You can also have little X models, which are quite similar, and in the context of actually extra dimension, you can have compactification, and compactification actually predicts that you have a tower of states of particles, of Kaluza-Clade states, and the lightest KK states can actually be a good dark matter candidate, and they also have specific features, in particular on the spectrum that is predicted from those kind of particles. So as for the production of WIMPs, I just want to have everyone on the same page and to recall what is the main mechanism for production, which is the thermal freeze-out. With the moment at which the particles, the WIMP, the couples from the thermal bath during the early universe is actually dictated by the equivalence between the interaction rate between WIMP's particle and standard model particle in the thermal bath and the expansion of the universe. So as soon as the universe dilutes so much the particles, then they cannot interact any longer, and then the abundance freeze out. And you can actually reconnect how the Hubble expansion scales with temperature, and usually the WIMP decoupling happens in the radiation-dominated era. So what happens is that you can actually talk about the comoving number density, which is the number density of WIMP per comoving volume, which is this Y here on the Y-axis, as a function of temperature. So as long as the temperature decreases, so the universe expands, you have that particles, if they are much smaller in mass than the temperature of the universe, are in thermal equilibrium, and then when the temperature of the universe drops down, they become non-relativistic. So actually the distribution of this particle in the non-relativistic regime is an exponentially cut off spectrum. At a certain point, when the dilution of the universe is such that cannot sustain any longer the interaction between particles, you have the thermal freeze out at a given temperature. And when the thermal freeze out occurs, is very sensitive to new physics through either the interaction rate, which determines what kind of interactions we have within particles, or through the number of relativistic degrees of freedoms that you have allowed. So to actually get to the final numbers and equations for the Rayleigh abundance, so the number of comoving particles that we have today from WIMPs, you have to solve the collision and Boltzmann equation, where you have the Liouville factor and the collision and Boltzmann factor. And you can work out the equation, probably Laura did in detail, and arrive actually to define what is the freeze-out temperature and what is as the relic abundance equation. So just to recap, for a non-relativistic relic, the freeze-out occurs when the particle is non-relativistic, as in particular when the mass of the particles divided by the temperature of the universe is much larger than 3. Actually, for a WIMP particle, this occurs around 20 to 30, for a value of x of 20 to 30. And the cross-section, as I was saying, determines when the decoupling occurs. And if you work out the expression of the comoving number density of particles at the freeze-out, you can obtain the well-known expression for the relic abundance as a function of the cross-section, and you can infer what we mean by WIMP miracle, because from the point of view of the calculation of the relic abundance, this occurs when the cross-section is of the order of the weak scale interaction. And for a typical candidate of 100 GeV, this is what you would expect in vanilla-like models for weakly interactive massive particles. So, of course, there are effects that complicates actually the picture, and the relic abundance and the cross-section at the moment of freeze-out are actually can be altered with respect to this baseline scenario by effect of co-annihilation. So, if you have a degenerate mass spectrum in your model, you can actually have particles that co-annihilate during and before the freeze-out. You can have threshold and resonances that occurs in the universe and before again the freeze-out, or you can actually be close to a pole of the cross-section. So to compute fully those kind of effects and get an accurate value of the relic abundance and the annihilation cross-section, you can rely on numerical codes, and you have actually hand-on sections about this. The two most used are actually Micromega and Dark SUSY. So, but one important question actually for indirect detection is, okay, so then we have this picture of the universe, so we know more or less which is a reference value. So you will usually find in books and in papers, scientific publication, often mention the thermal cross-section. So I just want to give you a glance of what we went with that. So the thermal cross-section is a reference value of the cross-section that the WIMP particle would need to have in order to meet the relic abundance constraint. Because in the end, we want to look for dark matter at the cosmological scale. So we want that our possible candidates is also the one responsible for the cosmology and is also the relic from the early universe. So typically in the vanilla-like scenario that I was mentioned before, the thermal value for the cross-section is this value here, so 3 and 10 to the minus 26 centimeters cubed per second, which would be the cross-section at which the dark matter would decouple. And if we look in the typical parameter space for annihilating dark matter, so here the cross-section, annihilation cross-section as a function of the mass of the candidate, you see here this gray line, which is the canonical value that everybody is quoting. However, the calculation is actually much more complicated than that. So it's not really a single value. There is a slight mass dependence, and in 2012, Steigman and collaborator performed the full calculation, and this is what you find now in papers. So usually this is the black line is the line, the reference value that we have for a WIMP candidate at different masses that would decouple in the universe through the freeze-out mechanism. The colored lines are actually the reach of current at the time searches for WIMP particles. So you see, and we will see that also afterwards, that current constraints, so for example, from the Fermi telescope in different channels and from the CMB here in yellow, start to carve down into the parameter space of the vanilla-like WIMP. So whenever you heard the sentence or you read the sentence, we are touching the thermal cross-section for masses of 100 GeV, it means exactly that if you have a typical candidate for WIMP for which the expected value of the radical abundance is described by these black lines, then the constraints start to get into this line and to probe this parameter space. Because I recall that usually when you have annihilation limits, everything, or in general upper limits, everything above the lines is excluded. So anything here is excluded and anything below the line is allowed. So as you can see here, for example, for the red line, this interval here on the black one would be already excluded or in tension with this type of observation. Is this clear? Because this is one of the main take-home messages, I think, of the old school. So if you have questions about that, just ask me now or even later, because I will be repeating this concept.
I have a question.
Yes.
For instance, here, why there is more sensitivity for bottom anti-bottom than up quarks, for instance? Is that possible to say?
So I think, and we will see that later, it's just a matter of kinematics and of actually the spectrum that you would expect. So the number of particles per unit energy that you would expect from a dark matter particle that annihilates into quarks or annihilates into B. So you will shift slightly the spectrum, and therefore you get different limits and different sensitivities.
And here, are you assuming a particular model like Higgs portal, or
no? This I think, because so this plot is taken from this reference, but they do assume standard annihilation into final states. You will see later what I mean with that, and generate the gamma ray expected signal through hadronization and decays from those particles. But it's like in the context of what I would call a generic WIMP model, in which you only care of the final states and you don't care actually of the mediators and really the interaction that leads to the formation of those final states. Will be clear, I think, later.
And sorry, and the last question is, what do you mean with this result, the continuous black line? The work that is in below?
The black line, you mean?
Yeah.
Okay, so the continuous line is actually a prediction for the thermal cross-section. So if you have in mind what thermal cross-section means, and this 3 × 10⁻26 value that you have, it was quoted for all masses. So actually, if you do the proper calculation, this is not just one value for all masses, but actually there is a slight mass dependence. So if you compute the cross-section that you would need in the early universe to match the value of the relic abundance measured today, there is a mass dependence. And the black line describes this mass dependence. So actually the thermal cross-section for WIMPs is not 3 × 10⁻26, but is rather this black line here. So for 20 GeV, it is something, I don't know, 2.1 × 10⁻26. For 4 GeV is 3 × 10⁻26. And for 1 GeV is 4.9 × 10⁻26. So this is the thermal cross-section. When you refer to what you do expect for a particle to be a WIMP, what would be the cross-section that it needs to have to match the relic abundance constraint?
Okay.
So it's basically a calculation that introduces the full mass dependence on the expected thermal cross-section. So if you want, you can just switch in your mind 3 × 10⁻26 for all masses with this line here.
Okay. Thank you.
That's clear?
Yeah.
Okay. Okay, so let me go ahead. Then the fact that dark matter particles interact with standard model particles somehow, and this is what actually drives the possibility to have the thermal production in the early universe, also allows us to look for signatures of those particles today. And you have probably already heard of the complementarity approach between different techniques that have been developed to look for WIMP particles. So you can actually look for the scattering of the dark matter particle against nucleons and nuclei in target materials in underground laboratories, and this is what is behind direct detection strategies. You can try to produce new physics particles at the colliders through the bouncing of standard model particles, and this is, I think, Geneviève Béranger gave you an introduction to that. And finally, you can look in the sky for the products of the annihilation or decay of those particles into standard model final states. And this is what is the basis behind indirect searches and the focus of my talk here. So indirect dark matter detection actually is based on, let's say, two key assumptions on the fact that dark matter should exist at the scales of galaxies and should also be the main responsible for their gravitational potential, and that somehow is non-gravitationally coupled to standard matter. So in this case, WIMPs are perfectly viable models that leads to signatures in direct detection, but they are not the only one. And Gabriela, I hope, gave also an overview of what are the possibilities to look for other type of particles and other type of models. So it's not only at the GeV-TeV scale that we can do indirect dark matter detection. The rationale behind the indirect dark matter detection is the following. So you have two dark matter particles that can annihilate, or one matter particle that can decay. And the decay annihilation goes through, let's say, standard model particles, which are quarks, leptons, and bosons, which we usually call final states, which are not stable. And through standard model interactions, they actually produce a showering of those particles, which can be photons at different wavelengths, but also other type of final particles. And what you get are fluxes of observable particles, which are stable. So you can get positrons and electrons that you can look for with charged cosmic ray observatories, or protons and antiprotons. Neutrino particles, again, there are searches dedicated to that. And what we are interested here are a showering of photons at different wavelengths. And actually what sets the interesting energy range where we look for is the center of mass energy available for the annihilation or decay process. So basically the mass of the dark matter particle determines what is the energy range at which we do expect the final photons from dark matter annihilation or decay. And in particular for WIMPs, which have masses between GeV to up to 100 TeV, then the photons emitted by prompt radiation would end up in the range between a few GeV up to 100 TeV. So, as I was saying, in the jargon, we refer to final states as quarks, leptons, and bosons through which the particle annihilate or decay. And so when you think, when you read, for example, annihilation into big quarks or taus or electrons and positrons, we actually meant the first step of the annihilation process. So what directly the particles annihilate into. And what I was explaining before is that somehow we are agnostic when we do indirect detection searches, at least in the feature-based approach, and we explain later. We are kind of agnostic of what occurs exactly between the dark matter particle and those final states. So we are not really care too much for searches about, for example, what is the mediator. But this will be important if we want to translate the results of searches into real models, or you want to do specific searches for specific models. Anyhow, so you can have annihilation into quarks with different branching ratios. So of course, if you have a real model, your model predicts through the Lagrangian and the couplings what is the branching fraction of annihilation into big quarks, for example, or annihilation into leptons. But if we are agnostic of what goes here, then the branching ratio are free parameters also for our phenomenology. So the energy is important to see how the energy is distributed within final states. So for example, if you have annihilation of dark matter particles into big quarks, then the largest majority of final stable states, so the ones that you can look for after the showering and hadronization process, are actually neutrinos, followed by photons and electrons. But if you, of course, have annihilation into leptons, like electrons, then there is not much space left for anything else. So you have basically only production of charged electrons and positrons. So this helps you getting an idea of what observables you can target with different final states. So annihilation into bosons and quarks generally gives you signatures in photons and neutrinos, but can be also secondary production, like a marginal production into electrons and positrons. If you have leptonic final states, like muons and electrons, then you can basically look for them mostly with charged cosmic ray observatories. And for the tau is a bit different because it has a semi-hadronic decay chain. So it's very much similar to what happens for annihilation into quark and bosons. The radiation that can be emitted by these particles is of different nature. So what I discussed so far, which is the chain of decay and hadronizations that comes out of quarks, lepton, and bosons, is what we called prompt gamma ray emission. So are the photons that are predicted to come from the standard model interactions that those final states undergo after being emitted. And I will describe how we can model this specific signal. But on the other hand, you can also have radiative emission from electron and positrons, or in general leptonic final states. Because whenever you have leptons, in particular electrons and positrons, then there are secondary mechanisms for production of gamma ray photons. And I think Daniele Gaggero gave an introduction of what are the mechanisms in astrophysics that can produce photons, and those are actually the same also for that matter. So if you have a source of extra electrons and positrons, or in general extra cosmic rays, natural processes that occur in the environment of the galaxy are inverse Compton scattering, synchrotron radiation, and Bremsstrahlung, and those can also produce additional photons. So in the following, I will go through the different parts of the photon spectrum and show you how we can combine them in the fully multi-wavelength emission spectrum from dark matter. So the starting point is the dark matter source there, which contains actually all the information that comes from the particle physics model, but also on the geometry of the distribution of the dark matter signal. So the dark matter source term is different from annihilation and decay, but is very similar in the end. So if you focus on annihilation, the source term, so the number of particles produced per, let's say, in the process of annihilation, is proportional to the annihilation cross-section of those particles in the, let's say, the galaxy today, the number of pairs of dark matter particles that you have, and the energy distribution of this particle is described by what we call the energy spectrum. So the number of final stable particles as a function of energy of this particle, weighted by some branching ratio. The number of pairs is directly related to the dark matter distribution in the galaxy, and you have received a lecture about that by several speakers during the school. And this the dark matter density squared, because we are talking about particle, and is the energy density actually, so it's divided by the mass squared of the dark matter candidate. The equation for the decay are actually pretty similar. You have to replace the cross-section, the annihilation cross-section by the decay width of the particles, which is related to his lifetime. We have now not the number of pairs, but the number of particles. So in the decay rate only scales as the density of the dark matter and not the density squared. And you have the same actually spectrum for annihilation, because the physics of annihilation into final state or decay into final state is exactly the same. It just changed the center of mass energy. So with the source term, you can actually compute what is the gamma ray emissivity. And from the gamma ray emissivity integrated over 4 pi along the line of sight, you can get the differential gamma ray flux. And if you work out this equation here, I won't just provide all the details, but you can arrive then at the equation that you have seen also in the other lecture for the gamma ray flux, and that we will see also in the follow. For the radiative emission, then actually, as I was saying, as soon as you have a distribution of electrons in your model, so and the distribution of electrons may come from like supernova remnants or pulsars, but it can also come from dark matter, then you can describe what are the expected signals in photons from this additional electron population. And you can compute again the gamma ray emissivity if you have the power for example, for inverse Compton. You can compute the synchrotron emission, and then you can get the final equation for the intensity. So let's have a look now at the spectra, because the spectra are very important to give you us an handle of what are the spectral features that we would expect from dark matter annihilation. And I will talk in the following about annihilation, and just I will come back rapidly on decaying dark matter if time allows. So if we take the source term, the energy distribution of the photons is described by this term here. In a like model independent approach, what we do effectively is to perform searches by fixing this branching fraction to 1 and discuss different final states. So in publications, you will see, for example, upper limits quoted for BB annihilation or tau annihilation or other final states. And these is what they meant here. So they fix the branching fraction to 1. And so their spectrum, the energy distribution of their signal is just described for annihilation into specific final states. And this is how they look like. So if we just look at the distribution of the energy of the photons divided by the dark matter mass, you have this dimensionless variable x, which is normalized to 1 because you cannot produce, there is a kinematic limit, which is the mass of the dark matter particle. And here on the y-axis is the dn dx, which is related, can be then retranslated into the D. You see what is the spectrum. So what we do expect, what is the spectral shape of this type of signal, so of the prompt photons that come from hydrogenation and decay. So this is for a fixed mass of dark matter. This is for a fixed mass of dark matter, but it's renormalized for the mass, so it doesn't really matter. So those are big quarks, and you see that the spectrum is pretty smooth and it's quite soft. So we said that the spectrum is soft if it has like an excess at low energies. While if you have tau leptons, again, I remind you that taus annihilate, have a semi-hadronic decay, and so 25% of the annihilation rate goes into neutral pions, so they produce a lot of photons. You have an harder spectrum, so you have actually an excess of photons at higher energy. And those are kind of the two extreme shape of spectral shape that you can get from the different final states, because annihilation into other quarks or bosons would look very much like annihilation into big quarks, so this kind of bump here. And annihilation into taus is something very specific to the tau leptons, and is a signal that can give you something which is much harder than what you get usually. So when you think at dark matter spectrum and also in publication, this is why usually you see paper quoting limits for taus and limits for big quarks, because there are kind of a benchmark for the spectral shape of the signal. So this is the spectrum from the prompt photons that you have if you just consider 3-level annihilation cross-section. However, you can have also emission of photons from higher order radiative corrections. And I will go into the detail of that a bit, because this is relevant for WIMP dark matter. So typically, the annihilation cross-section can be expanded in powers of the velocity. And in the galaxy today, and also in other targets, but in the present universe, the dark matter particles are in a non-relativistic regime. So if exists the A term, which is also the S-wave component of the annihilation cross-section, is the dominant contribution, because then anything is then suppressed by powers of the velocity. However, there are models, and especially for WIMP in supersymmetric context, where the cross-section the S-wave contribution is actually suppressed. And this occurs whenever, for example, you have a WIMP particle in a SUSY context of neutrino particles annihilating into fermion, so a fermion-antifermion pair. And there is a suppression of the cross-section, which is proportional to the ratio between the mass of the fermion, the final fermion, and the mass of the dark matter particle. This is exactly what occurs for charged pions and for their annihilation to leptons, and also the mechanism behind it is very similar. So this is standard model physics, but what you can do is to measure actually what is the rate of annihilation of decay of the pion, of charged pion, into electrons and electronic neutrinos, or into muons and muons antineutrinos. And this is very much suppressed, and is suppressed by exactly the ratio of the mass of the electron divided by the mass of the muon squared. So the reason is because the state of the pion is a spin-zero state, and it would like to decay into right-handed muons and right-handed neutrinos. However, weak interaction only couples to right-handed antiparticles and left-handed particles. So this process here is highly suppressed, and the rate of suppression is again proportional to the mass of the fermion divided by the mass of the pion squared, which is exactly the same thing that occurs for annihilation of say, neutralinos into final fermion antifermion pairs. So the cross-section at 3 level is naturally suppressed, so which means that this kind of process, annihilation into fermion, receive perhaps important contribution from higher order corrections. And what I meant by higher order corrections are like a QED process that occurs and have a photon or a boson emitted for different legs in your diagram. So you can have initial state radiation, final state radiation when the particle is emitted from the final legs, or what we call internal bremsstrahlung. And what has been demonstrated in the literature for different kind of additional particles emitted is that usually the higher order annihilation cross-section, so the 3-body final state annihilation, is much larger than the 2-body one, because the 2-body one is helicity suppressed. And not only that, it also presents spectral features that might be relevant for the search of this type of signals. So if you have an additional photon emitted in the 3-body process, so now we are talking about dark matter that emits fermion antifermion pairs plus a photon. The photon can be emitted either from the final state legs, so it's called the final state radiation, and you can actually show that the spectrum is very model independent because only actually depends on the standard model physics of what happens into these final states, while the virtual internal bremsstrahlung, so the emission of a photons from the mediators, of course, depends on what is the model that you are considering. And it can lift the helicity suppression, for example, for T-channel diagrams in neutralino models, but also in for models of Kaluza-Klein particles. And what you get is typically a spectrum, which is here for Kaluza-Klein and here for a neutralino in a specific part of the parameter space, is a spectrum that presents alteration at the high end of the spectrum. So what I meant by that, so if you look at the expectation from the S-wave production, so without this final photon added, is this dotted line here. But if you add this final photon, then what you get is, you see here, a sharp cutoff at the high energy end of the mass spectrum. And a sharp cutoff is something that we can actually use in dark matter searches. And I will give you some example. The same holds for neutralino in a specific part of the parameter space, where you have that usually from the decay and hadronization, so the BB and taus that I've shown you before, you would expect this dashed red line, but if you allow for virtual internal bremsstrahlung, in particular in this type of models where this is relevant, you get an additional contribution from this higher order correction, which gives you not only an enhancement in the annihilation cross-section, but also a sharp spectral feature at the high end of the energy spectrum. So you can you can play the same game. It's not much fun, I would say, also for emission of weak bosons, electroweak bosons, so W and Z and X's, and work out what is the full phenomenology of the additional final states. In this case, when you have electroweak gauge bosons that are emitted, or X's, those can also be emitted from the initial legs. So on top of final state radiation and virtual internal bremsstrahlung, you have also initial state radiation that can help you in lifting the helicity suppression. You can work out all the diagrams. This was my PhD thesis, and you can actually show what are the signatures of this type of additional corrections. And this is just an example, so to give you an idea that in the context of model-dependent spectra, you can have modification of the spectra that may be important for actual searches. And you can see here again this energy distribution as a function of the energy distribution as a function of the energy of the particle for different final states. Those are leptonic final states, and you can see here that from electroweak and electromagnetic radiation, what you get is an enhancement of the spectrum and a modification of it at the high end of the spectrum. And if you look at photons and antiprotons, is again very much similar. So in particular for photon, which I'm mostly interested in, electroweak and electromagnetic radiation, additional radiation gives you these spectral features, which come mostly from electromagnetic corrections, but also some changes in the spectrum at lower energies. So you can actually exploit this, and I will show you how. The prototypical example of spectral feature is actually the gamma ray line. And I present it only now because actually the gamma ray line is, in generical models for WIMPs, is something that is suppressed at loop level. So it comes after the three-body process because it's actually a four-body process. So you have annihilation directly into two photons through a loop, because you cannot have direct annihilation into two photons being a dark matter neutral particle. And what you can actually predict is a gamma ray line, so it would be a delta centered at this energy, which depends on the particle emitted, because you have production of two photons, or a Z and a photon, or an X and a photon. And the line, if you look then at the flux as a function of the energy, instead of a delta, observationally would look like a Gaussian, because it's kind of smeared by the energy resolution of your instrument. And you see that depending on the energy resolution, those are just benchmark value for the energy resolution, you can have something that is quite narrow or something that is much broader. And this is one of the, together with spectral features coming from higher order correction, are one of the most smoking gun signatures for the spectral distribution of WIMP particles, because you wouldn't have actually almost any astrophysical process producing this type of signatures. People in the literature have also studied other type of gamma ray features, which are, for example, when you have annihilation into for photons mediated by some lighter state. So this is in context of some modified WIMP scenarios. You can have actually box-like spectra. You can see here an example. So typically your gamma ray signal would look like a box smeared out by some energy resolution. So in the end, how does the photon spectrum look like is depicted here. Again, this is the spectral energy distribution as a function of the energy of the emitted photon, always renormalized to its mass. Here are it's the emission from the soft quarks, bosons, that would give you something which is anonymous, like a bomb. And then in most models, what you predict are sharp spectral features, lines, box, orbital internal bremsstrahlung features that you can look for. And I will give you an example of how line-like searches are designed and optimized to look for this type of spectral features. So in general, how to compute the spectrum, again, boils down to some numerical codes that have been developed. You can use like SUSY, Micromega. There is also a Mathematica package, which is the PPPC for dark matter indirect detection. And how actually this is related to standard model physics. For the showering and anonymization actually depends on Monte Carlo generators, and there was a nice work by Sembranos and collaborators comparing different Monte Carlo generators to get uncertainties also on the bump spectrum that you get from anonymization and decay. Any question so far? Otherwise, I will move on.
Yeah, could I ask a question, please?
Yes, sure.
So it's with regard to the branching ratios. So Earlier you said that, especially with regard to indirect detection, we just use one channel and assume 100% of annihilation into that. I was just wondering, like, why we do that. Do we expect dark matter to just go into one channel, or is it too difficult to model other branching ratios as well? Yeah, could you tell me a bit about that?
So perhaps just wonder if I should go directly to one slide. Let me just, I think it's important, and it's something that I actually would like to tell you. So, and I don't know if I will have time, so I will just go a bit at the end. Let's see. Okay, so this changes a bit my presentation, but it's not a problem. What I want you to take home is a fundamental difference on like the phenomenology and the searches that we can make. So on the one hand, we have dark matter models, right? We can work out the full, I mean, we have the Lagrangian, we have the full prediction for the signal. We know for any model that we have, we can predict what is the branching fraction in different kind of final states, and we can predict what is the DNDE without caring about what are actually the branching fraction. So the branching fraction are something that we compute in full WIMP models. This is clear for everyone? I suppose yes. So on the other hand, we have data, and we want to compare with data, and we want to derive some implications for WIMP particles. So what do we do when we do a search is that we don't really know for what model we are looking for, right? So what we assume effectively is that dark matter annihilates into predominantly into a final state. And this is not too off, because there have been works for neutrino dark matter, for example, showing that in specific, I mean, in the region of the parameter space that are still allowed by other constraints like collider and direct detection, you do actually expect dominant annihilation into one specific state. This does not mean that there are not points which are perfectly allowed, in which you have a combination of branching fraction and the spectrum maybe looks something very different. So what we do when we do searches is that we cannot, of course, cover the full zoology of the models, but we take benchmarks, which we think entails the general phenomenology of different WIMP models. And in this respect, we test several spectra. So we test BB with respect to taus. We provide limits for that when we look for bump-like features, or we look for specific features that would arise into those models, which are, for example, line-like signals. And you can set limits on the line emission. So this is what I would call the feature-based approach, which remains kind of agnostic behind the model, because in a certain sense, you want to be generic when you perform searches, because you don't want to throw away anything. But if you have a model, a specific model for which your spectrum look very different, nothing prevents you of using the real DNDE that you would get from that model, weighted from different branching ratios, to look for this specific signal. So for example, if you have limits from dwarf galaxies, the DNDE element is just like a parameterization of your signal that enters in the prediction of the number of photons that you would expect and you go to look for. But it's not really, it's something that you can change. I mean, so if you have the data and the pipeline to analyze the data and to get upper limits, then you can replace that with whatever you want. But the way in which the community works and has agreed somehow to present results is for them to be generic and to having phenomenological implications for different models that can be recast by people actually working on the specific models. Is it clear so far? So this answer your question.
Yeah, that cleared it up a lot. Thank you.
Yeah, and so why I have introduced this concept. Let me just explain you what I mean with this model versus feature-based approach. So the feature-based approach is what would be 90% of my lecture, because dark matter features can be studied one at a time, and you can exploit them to design specific searches, optimize them to look for general WIMPs, but it doesn't really mean that they are very predictive. Actually, they are not. So if you want something that is predictive, you have to have the full model. And once you have a model, a complete model, then you can also link different observables. You can look at the complementarity between the different search strategies, direct, indirect, and collider searches, and you can eventually break the generalities into the parameter space if you ever see a signal. So let me just give you an example of what you cannot do with this feature-based approach when you have a signal. So you have heard from Gabi's lecture about the Fermi GV excess. I won't give any detail about that. I just want to say, so you have a signal which can be actually, this is the energy distribution of the signal as a function of energy. And those data points here are some characterization of the spectrum, which I have derived in the past. So what you can do is then if you want to interpret this positive signal in terms of dark matter, you can fit it with different dark matter final states. In this feature-based approach, when you are agnostic about the final state, then you can fit with different final state channels, assuming 100% branching ratios. For the leptons, you can include secondary emission. But what you realize is actually that for this specific signal, so the galactic center excess, there is a degeneracy between different final states and the energy distribution that your data gives you. So you can fit those data points within the systematic uncertainties that you have with different final states. So it can be a 10 GeV dark matter particles annihilating into taus, but it can also be a 125 GeV dark matter annihilating into x's, and this is the spectrum that you would get. So perfectly fine within systematic uncertainties. So this means that based only on indirect detection results through a feature-based approach, there will be some degeneracies that will be left if you ever find a signal. So how you can actually break the degeneracies if you see signals, then you have to go full model. And to go full model, what you do is that you have your model that predicts all possible observables. You can do what are called global scan into the parameter space, and you can derive what are the points into those global scans that are allowed by different observables. So this is just an example from this reference here, where they assume that you have a signal in indirect dark matter detection of a 25 GeV particles with this kind of annihilation cross-section into big quarks. And if you just look at the parameters, allowed parameter space only from indirect detection results, are the blue points here. So you see that the reconstructed region in the parameter space, which is what eventually you want to pinpoint. So what is the mass of the signal that I have seen? What is the annihilation cross-section? Is this region, this blue region here. But if you, on top of this signal in indirect detection, you also have a signal in indirect detection, and this is the example of oxynon one-tone signal, positive signal, then again, you can perform the reconstruction only with direct detection results, and these would be the brown points here. If you combine them, so this is called the complementarity approach, then you break the degeneracy, and you can actually get a better determination of the mass and the annihilation cross-section of the signal that you have seen. And this is only possible if you have a full model. In general,
I'm sorry?
Yes, sir. Yeah.
Could you come back to the previous slide?
Yeah.
So
This one or the one after?
Sorry?
This one?
Yeah, this one.
Number 83. Okay.
Yes. So in the right plot, you have different channels. Actually, what is A in the y-axis of the second plot?
A is just an astrophysical factor that accounts for the uncertainty on the
Okay. Okay.
on the dark matter density.
But it is supposed that all the colors here or the curves satisfy or fulfill the relic density abundance for each channel?
No. So this is based only on fits for the galactic center excess. So you only look at the specific signal and the implication in this parameter space. But you don't, I mean, we haven't looked at the full WIMP scenario, like having also relic abundance constraint included.
Okay, so in the same way that in the next slide, you did a complementary approach based on indirect detection and direct detection. You can also use a relic abundance in order to find the appropriate region.
I think yes, you can include it. Yes, you can include it as an additional constraint, and and then if you recall the thermal value that we were discussing before, I mean, it will a bit depends again on the model that you have, but possibly like quark final states will be in the right ballpark to give you the right relic abundance. I have no idea for the X.
And my last question is in the left plot.
Yes.
Okay, you are talking about an excess that occurs around those energies. But what is the background there? Or you need another plot to see that? Because I see a bump, a kind of bump, but I cannot see clear where is this excess.
Okay, so I don't have any slide about the galactic center at all except this plot here, because I've seen Gabi's slide and I think she discussed it. But the point is that what you see here is the spectrum, so the photons, the spectral energy distribution of the photons that constitute the excess emission towards the galactic center. So you don't see the excess in this plot here. Because what you do is actually to look towards the galactic center region with Fermi-Lat data, to collect the data from that region. And then you do a full, what is called template analysis, when you have a full model for your gamma ray sky, in which you have inverse Compton emission, Bremsstrahlung emission, Pi-zero emission, and all the processes that you do expect from the astrophysics of the galactic center environment.
Sure.
When performing this kind of spatial analysis, and partially spectral also, what has emerged during the last 10 years is that there are photons which cannot be associated to any kind of astrophysical template that we put into the analysis. And so those photons that remains as residuals in a model with standard astrophysical background are called the GV excess. And if to explain this kind of excess photons, you need an additional template in your model which has a spatial distribution similar to what you do expect from dark matter. So in a typically cusped profile, like Navarro-Frankel-White, a bit more steeper. And the spectrum, so if you look at the energy distribution of those additional photons, is this distribution here. So the bump here that you see is actually only the data of the excess.
Yeah.
You see, is not the full data. The full data, the total data would look like something very like a power law at the level of 10 to the minus 6 here, and would be well fitted. I mean, the 90% of the emission from the inner galaxy comes from ICS and pi zero emission. So the total data would look like the sum of those two linear. But the 10%, there are 10% of the photons that you cannot explain other than adding an additional template, and the distribution, energy distribution of those additional 10% of photons are those data points here. So in the end, you can fit the excess with, then the question is how you interpret this excess emission, and people have argued that one possible interpretation is dark matter, and so that's why you can fit this excess emission with a dark matter spectrum, and the results you would get in the parameter space is this one.
All right.
Is that clear?
Yeah, totally.
Fine.
Thanks.
Oh, you're welcome. Okay, so this was actually one important point.
I think you have a question, Francesca, also in the chat window, just in case you.
Sorry, I haven't seen it.
No problem.
So I'm not a expert, so that I think all of you see, but I can repeat the question. Why is the interaction of a possible graviton not considered in the dark matter particle model, or is this not a possible option in the light of the data? I'm not an expert on gravitons, and I have no idea what would be a possible signal from at GV energies. So apologies, I can talk about gravitinos, which are, like, again, good dark matter candidates, and would be example of decaying dark matter. For the graviton, I'm not sure. Miguel, you do you know? Because perhaps
less than you. I'm even farther, I think, in the topic. Sorry.
Okay, fine. So apologies. I will probably, I will get some more information, and if you want to write me an email, I can look for that explicitly. Or if you have a model in mind, you can also write me, and I can have a look of why this is not interesting, or why it is not being addressed by the current literature. Okay, let's go back to where we were. Here. So for me, it was very important to give you this feeling of feature versus the model-based approach, because in the end, everything boils down on having something more model-oriented or something more phenomenologically oriented, and well, it's a matter a bit of taste and what your research lead you to. Okay, so let's then see what is the dark matter gamma ray flux, that the master equation for what we do expect. So the number of photons per energy in a given direction of the sky, which is described by the solid angle, so basically the LB coordinates, the given energy, is given by this master equation here, which you have seen already probably many times, where you have a particle physics factor, which I already discussed, and a geometrical factor, which is related to the distribution of dark matter particles in the target you're interested in. And once you have a prescription for the DND, so the spectral energy distribution, you can translate that into flux space, where you can actually overlay also some data. This is just a sketch to give you a feeling of what the different parameters are responsible for. So you have a flux here in typical units that we have. So this is the energy flux as a function of energy. This is the dark matter signal that you would expect from some typical bump-like spectrum. The annihilation cross-section actually governs the normalization of the signal, while the dark matter mass is related to where the signal just fades down. So you can have bumps which are shifted more on the right or more on the left, depending on the dark matter mass, and the normalization is driven by the annihilation cross-section. And typically, as for the same way as for the GXS, the data are well above the predicted signals, and you have, of course, some astrophysical background. There is a caveat here. This master equation holds only if you have a S-wave approximation. So if your annihilation cross-section is dominated by the velocity-independent term, if you have a velocity-dependent cross-section, this equation changes, and actually you have to fully integrate over the phase space velocity of the dark matter distribution in the target of interest. I have slides of them, but I'm not sure I will arrive to them. But this is an important point to keep in mind. So the signal crucially depends on the J factor. Céline Combet gave you already a very nice lecture about that, so I won't spend too much time. The astrophysical J factor depends on the integral along the laser side of the dark matter density square, or the dark matter density in the case of the D factor, so for the decaying dark matter, and is one of the main theoretical uncertainties that we have if we look, for example, at signals from the galactic center direction. On the other hand, for other type of targets, they are less affected by the different spatial distributions. On top of the smooth galactic halo, simulations of the galaxy formation nowadays with fully hydrodynamical simulation predicts the formation of substructures, so clumps of dark matter, so overdensities of dark matter at small scales embedded within the main halo. And what you can do is to take a simulation like this and to generate what is the predicted signal in gamma rays. So if you look at the galactic projection of the sky in longitude and latitude coordinates, here is the galactic center. So this is the expected gamma ray flux from the main halo in a typical simulation that we used in 2014. And you see that the signal, the color bar represents the number of photons or the flux, in this case, is picked towards the galactic center because you have a cusped profile for the main halo, and then it fades away at higher latitudes. But on top of this, from the same simulation, you can predict what is the distribution, or what is actually the expected gamma ray flux from every single subhalo. And in this case, the gamma ray distribution would look like something like this, which you would see bright hot spots in the sky, and how much bright they are depends on the annihilation cross-section. So besides spectral features, there are also spatial or angular features that come either from the main halo or from the presence of subhalos in the galaxy that you can exploit. And there are methods that have been developed in order to leverage onto the specific type of signatures, like looking for anisotropy or cross correlations. And I will just describe how we look for those dark subhalos in the galaxy. So as for the radiative emission, those are the same mechanisms that holds for normal astrophysical processes whenever you have a source of cosmic rays injected in the environment. So either this originates for dark matter or from like normal sources, the mechanisms at place are always the same. So you can have inverse Compton from low energy photons from the interstellar radiation field, starlight or CMB, or infrared light, which is upscattered by an electron. So in this case, it would be an electron from dark matter. It is upscattered up to gamma ray energies. Or you can have Bremsstrahlung onto the interstellar medium. Or you can have synchrotron radiation, and especially if you have electrons and positrons emitted at GV to TeV, as this is the case for electrons from WIMP dark matter, then given the magnetic field of the galaxy of the order of the microgauss, then you would expect a signal at radio wavelengths. And so the predicted signal from dark matter annihilation is fully multi-wavelength. So if you have a typical particles, I think here is like 100 GeV particles, actually depends a bit, so the 3 lines are for different dark matter particles, annihilating to be quarks, you get the pi0 bump, so those prompt emission that I was discussing before, at energies of at TeV scale, it's GV to TeV scale. But then you can get secondary emission through those radiative processes from the electrons that are also produced during the annihilation shower. And you have the peak of the inverse Compton on starlight here at a few MeV, 100 MeV, and then you have inverse Compton on CMB at even lower energies, and finally the synchrotron at radio. So you can actually exploit this kind of multi-wavelength features to look for a dark matter signal. So what I want to discuss in the following is how we look for those features with some typical examples of analysis of Fermi-Lat data. So different searches leverage on different WIMP features. Those are very general and again enters in this kind of approach which is phenomenologically driven. So generally most of the searches towards different targets look for this smooth bump-like signal coming from the prompt emission towards the smooth galactic halo. And here it's very important how you model the astrophysical background because there are a lot of degeneracies either with the astrophysical background itself, and you have to be very careful not to overinterpret possible excess. You can then look for spectral features, and you can design searches that are optimized to increase the sensitivity of your instruments towards this specific signal, or as I was saying, you can look for some target or spatial feature. I will give you like 3 examples that combines those type of searches. And so the first is the search for dark matter in the isotropic diffuse gamma ray background. The second one is our searches towards gamma ray lines. And finally, this is is not really exploiting the angular features, but to give you an idea of how we look towards specific targets. And we also exploit the fact that we expect subhalos in the galaxy. So let's start. I will go a bit quicker here because the concept is very similar to what occurs for the galactic center excess, and probably Gabi has explained that in quite some details. So what do I mean with high energy, with high latitude diffuse gamma ray background? So this is the sky as seen by Fermi-LAT after 10 years of operation, where the different components have been already described to you by my other colleagues. What I want you to take over here is that you can focus on higher latitudes, so cut away all the bright emission, which is very much contaminated by the astrophysical processes of cosmic rays in the galaxy. You can consider only photons that comes from high latitudes, and if you do so, you can subtract the known astrophysical backgrounds, and in this case you see that there is not much related to the galactic diffuse emission, but the main astrophysical background is given by those bright spots here, which are identified sources. And if you subtract, it's a bit more complicated than just subtracting, but if you subtract these kind of known contributions, then you can build the spectral energy distribution, again the flux as a function of energy, of what we called isotropic gamma ray background, or better to say diffuse gamma ray background, since small anisotropies, so fluctuation in this diffuse emission have been found. So the spectrum of the EGRB, I will call like this for now, can be parameterized by a power law up to 10 to the let's say 10 to the 5 to 10 to the 5 MeV, where you have a cutoff due to the absorption of the extragalactic background light. So this is the phenomenological characterization of this type of observable. But what is the nature of it? So the origin of the EGRB can be quite variegated, because you have to think about it as originating from all the extragalactic emission that you can have in gamma rays. And this may come from sources that you don't see, so they are not bright enough to be detectable by the LAT as hotspots, but would contribute through their cumulative emission as unresolved populations. And so you can have several classes of candidates, and people have actually made an effort in trying to estimate what is the contribution to the EGRB, starting from the resolved counterparts, in order to have an idea on how much, for example, blazars contributes to the EGRB emission. And then you can have what we call truly diffuse processes. So those are processes which are not related to point sources, but are related to like more smooth distributed emissions, like for example, dark matter in the galaxy, or from the all other external galaxies, would give a contribution to this IGRB. And so the search for dark matter in the IGRB is actually based on this possibility here. And there was a nice review by Miguel Angel and Mattia Fornasa in 2015, trying to summarize a bit what was the status at the time of the searches towards the EGRB, but also in particular making a focus on the astrophysical modeling of this type of emission. So those in black are the IGRB data, and the different colored lines are estimates in the literature from different people of the amount of astrophysical emission that you would expect from different classes of unresolved objects. So blazars and misaligned IGNs and star-forming galaxies, if only based to the models that were available at the time, but I don't think the paradigm has changed so much nowadays, basically oversaturates already the IGRB. And then you have mid-second in the galaxies, which can only contribute a few percent to the high latitude emission.
Excuse me?
Yeah.
I don't understand very well which of these sources corresponds to the galactic or our galaxy, and which of them correspond to extragalactic? Yeah. Could you repeat that, please?
Yeah, sure. So here I was glancing quite quickly on it, but you have the main classes of objects that are actually detected as point sources by the LAT. So by far the largest, the most abundant population detected by the LAT as point sources are blazars, which are extragalactic objects. And as extragalactic objects, you have also star-forming galaxies and misaligned AGNs, are active galactic nuclei, which are not beamed towards the observer. So those three classes are actually extragalactic objects. And in the galaxy, what you have are supernova remnants and pulsars mostly. Why supernova remnants and pulsar nebulae have not been considered for interpreting the IGRB is that their distribution is very much confined into the disk, while there is a population of galactic objects, which are pulsars and millisecond pulsars, which have been found also at higher galactic latitudes. So you have detected point sources of this class also above 10 degrees in latitude and below. And so those potentially could have been interesting and give a contribution to the IGRB. And this is why they have been considered for estimates of the galactic contribution. So the red one would correspond to the galactic contribution, basically, because you don't have many other source classes that can make the job at high latitudes, while all those classes here separately comes from different classes of extragalactic objects.
Okay, perfect. Thanks.
You're welcome. So what you can do then is to ask the question, okay, I have this data at high latitudes, I have this modeling of the astrophysical populations, and this is a guarantee. Okay, there are uncertainties on this modeling of those classes, but we know that there should be a fraction of the IGRB that is due to unresolved objects, because you see the resolved part of the luminosity function. So you do expect that those objects are also fainter than the ones that you resolve individually. So you can ask the question, how much room is left for a dark matter signal from the galactic halo? This is a kind of old work, but it's just to illustrate you the idea. So what you can do is you have the data and you can combine the astrophysical models that you have in order to get optimistic or conservative scenarios on the astrophysical emission and derive constraints on dark matter. So this is typically what we do when there is nothing better that we can do, basically. So you have, you usually define conservative scenarios, which leads you to limits that are robust. So it's very difficult to further push up those limits. So when you read conservative, this means a limit that is very difficult to push further up with the modeling that is made. So, which means that in the conservative scenario, you want to have the largest possible signal of dark matter allowed, meaning that you have to push down the contribution from the astrophysical emission. And if you then look for different channels for, this is a typical profile for the galaxy, which is scored, but is not important here, you can derive limits on the annihilation cross-section as a function of the mass. And then you can be optimistic, and usually people present in paper like conservative scenarios and optimistic scenarios when they don't really know how to take better into account uncertainties. Whereas that you can, for example, in this case, use the best fit results for all the different contribution to the IGRB. So you use the best fits, so you combine them, and you get very optimistic limit in which you have like a higher astrophysical background, and so the room for dark matter is less and less, and here the constraints on the dark annihilation cross-section are stronger. This was just an example for the galactic signal. What I said before is that you can also consider extragalactic signals. And in that case, there are, prescription in the literature on how to fully model basically all the external galaxies that could give contribution with their dark matter halos. And what is very important is this parameter here, which contains basically the degree of clustering of dark matter at a given redshift. And there are different approaches that have been developed in the past based on the halo model or on the power spectrum model. And all of them have kind of issue in extrapolating at the smaller scales, because also based on simulation or observations, we only can get a hint or an idea of the behavior of the dark matter clustering, so the number of galaxies per unit mass for halos, let's say, more massive than 10 to the 6, 10 to the 7 solar masses, but then extrapolating to lower masses, is a matter of either having simulations and being able to build, for example, the concentration mass relation down to smaller scale, or to somehow extrapolate at smaller scale with some educated guess. If you do so and consider the extragalactic emission, then again, those are your data. This is the green line is some expected astrophysical background, and this is the dark matter signal from the galaxy and from the outer galaxies. And you can again derive the limits on dark matter for different assumptions on the modeling of external galaxies that you have. So the modeling of, say, subhalos in external galaxies are, again, one of the main theoretical uncertainties when you discuss about an extragalactic signal. So this is as much for let's say, prototypical search for bump-like signals. What I want you to give you now is just a feeling of searches for gamma ray lines, because they work a little bit different from the point of view of the analysis. So spectral features, as I was saying, have an advantage from the point of view of the type of search that you can perform, because they are not very much degenerate with other astrophysical backgrounds. So in one case, which you don't have spectral features, you have a generic bump. A spectral features would instead look like something very sharp and narrow. So you can explicitly look only for this kind of signatures with methods that basically slide the different energy ranges in small energy windows, and look for deviation of the data points with respect to a smooth power law. So you can assume that if you do your binding finer enough, you can have a good approximation of the background as a power law, and on top of the power law, this power law here, you can look for a dark matter line signal. And if you have a line, it would look like a small excess in your smooth power law. This type of search was quite some excitement around 2012, when a line signal was found with an excess of 3 sigma global significance towards the galactic center direction. This was called the 130 GeV line, because it was for a mass of the dark matter particle, could be interpreted for a mass of the dark matter particle on 130 GeV. So it's not really important then on the historical procedure, because basically this line really went quickly, was resolved to be a statistical fluctuation. and no signal is any longer there since 2012. But what was important is that now you also find analyses that are currently updated by the collaborations, either at the GV or the TV scale, for looking for line signals. So on top of the traditional plot annihilation into big quarks of 2000, you also have a dedicated publication on limits on the lines as a function of mass. And this is one of the latest publications from Fermilat. I think it's not the latest one, but it's just to give you an idea that no fluctuations were found any longer. And you can also do the same thing with Cherenkov telescope array, and those are the limits from S, again in 2016. So in the, let's say, 10 minutes that I can take 10, or I have to cut sharp at 45, Miguel?
No problem, you can take 10. That's not a problem, Francesca.
Fine. I will talk about how we look for dark matter towards dwarf world galaxies, and then dark subhalos. So again, not much of an introduction here, because Céline has already discussed about dwarf world galaxies, and now we can get the J factor from the direction of those objects. From the point of view of indirect dark matter detection, what is really interesting here is that from optical surveys, we have identified those kind of objects that are thought to be dominated by dark matter. So a natural question to ask is there an excess gamma ray emission on top of the astrophysical background that we do expect from their direction? And the nice complement that they have is that they are many, and that they can be used as independent target and combined together. So usually you have, as I said, the position from the optical discovery. You can actually then look into gamma rays and collect all the photons that comes from the specific region of interest. And what you can ask yourself is, again, is there any excess emission which could be attributed to dark matter on top of the astrophysical background at the dwarf position? So far, no detection has been found, so from any of them. So what you can set is, again, limits on the annihilation cross-section as a function of the mass. But as I was saying, on top of that, you have the advantage that you can combine those targets as being independent in a joint likelihood and weight them by their astrophysical factor, so the J factor, and also marginalize over it. And you can get what is called a stacked constraint, so a combined constraint in a fully joint likelihood analysis. So the status of the limits from dwarf is the following. If you consider the parameter space and Fermilat official analysis, I recall here that this gray line here is what we expect from the thermal annihilation cross-section in this work of 2012, so with the full mass dependence. And you see that the Fermilat analysis really starts to exclude vanilla-like WIMP starting from 100 GeV down to smaller masses. However, you have to keep in mind that there are always systematic uncertainties also for the most robust searches that you can perform. So although dwarf are very little affected by astrophysical emission within the dwarf itself, because we think there is no gas actually to produce a secondary emission or sources that can affect eventually the limits, you can have quite some uncertainties in the J factor determination. I don't know if Céline discussed all of them, but there are effects that also can weaken the limits because basically alter the derivation of the J factor. And must also, in a competitive way, you can also have uncertainties in how you evaluate the background due to the galaxy at the dwarf position. And so you can actually weaken those limits by a factor of a few. This was just to illustrate that you can also have systematic uncertainties on targets that are usually thought to be quite strong in setting constraints on dark matter. So in the future, what you would need to improve would be, of course, to observe longer, but only with Fermilab, the improvement cannot be so huge, like a factor of 2 to 5 in 15 years. But what you do actually expect is that with the future variable observatories, which should start to take data soon, you can increase the number of detected sources, especially what we call ultra-faint dwarfs, and improve also the determination of the factors. And this would give you more targets to look at and possibly a better sensitivity into the parameter space. As I was saying, beyond the dwarf, which have optical counterparts, the standard galaxy formation through hydrodynamical simulation also predict the formation of dark halos. So in a full dark matter simulation, you have some of the objects that are able to form stars, and those will be dwarf-like halos, but some of them would have either a stellar content which is too faint to be detected by current optical surveys, or be completely dark because they couldn't really trigger star formation. However, if those are subhalos of dark matter, they could in principle emit photons through the mechanism of annihilation that I described you before. And so the question is, do we have already detected dark subhalos in currently unassociated gamma ray sources? And there were several studies looking at how you can constrain this type of subhalos. So there are two main steps in this type of search. One is to identify the number of subhalo candidates in the data, in the detected sources of Fermilab, and this usually works quite well with machine learning algorithms for classifications. And then if you want to interpret that in dark matter models and give actually some kind of upper limits on the dark matter parameter space, you have to compare the number of subhalo candidates with the number of subhalos that you would expect from your subhalo model that have a flux higher than the LUT threshold to those type of objects. And so if you look here, this is the distribution of J factors as a function of mass of the subhalo. This is the full population of subhalo for some specific subhalo models, which are not important the details, but you will have always a population, a part of the population that is too faint to be detected, and the part of the population that would be detectable as point sources, so could eventually be compatible with some of those candidates. And if you compare the two, in order to match them, you have to tune the annihilation cross-section, and you can derive upper limits due to the fact that you have a given number of subhalo candidates in your catalog. And there is a fundamental reach of this type of search, because of course, once you reduce at zero the number of candidates, this is the strongest limits that this kind of search can give you for the specific catalog. Let me conclude just with an overview of what I wanted to say in the lecture, and perhaps if you have questions, I can elaborate a bit more on the different points. I wanted actually to mention that you can put all the constraints on the same plot, but you have to be very careful not to overinterpret this kind of plots, because every constraint from different targets comes from specific uncertainties, systematic uncertainties mostly, and different targets will evolve in a different way, in a sense, because you have targets whose reach will be systematic dominated, others statistically dominated. So how in the future limits from different targets will be derived will basically depend also on our knowledge of better modeling the astrophysical background. You can push further down the limits for dark matter to sub-GeV WIMP particle, but here we have basically a gap in the sensitivity of the instrument, which is called the NIV gap, and we have to wait for future mission in order to be able to fully exploit the potential of this kind of searches. Or you can push further up your search with Cherenkov telescopes, and in particular with the Cherenkov telescopes array, which is supposed to improve the search for dark matter of about a factor of 10 towards the inner galaxy. And just for you, because I think this is also a point that often is not addressed in lectures, because we have too much material to have, is that when you go to TV scale, then typically, if you think about WIMP, which are the mediators are electroweak bosons, then is not any longer valid the contact type approximation for the interactions, which were valid in the GeV range, because the dark matter mass is not much larger than the mediator mass. And so there are not perturbative effects that comes in and manifest themselves as long-range interactions. So there are in particular two effects that are velocity dependent and are important to take in mind, which are the Sommerfeld enhancement and the possibility of bound state formation. The Sommerfeld enhancement has to be included for any WIMP signal. The bound state formation was shown to be not very relevant in terms of boost that can give to the cross-section for WIMP, like neutralino, like WIMP, but it can be important for non-trivial light dark sectors. So this is how I would have described the thing, but let me just go here, because I will conclude with the fact that we have seen just everything under the velocity-dependent cross-section, but I invite you to take a look at the slides that will be online, because in generic models, for example, with Sommerfeld enhancement or with P-wave annihilation, where the S-wave is suppressed, the cross-section can be parameterized by a factor which is velocity dependence, for example, the Sommerfeld enhancement factor, and a term which is velocity independent. So in that case, the flux of gamma ray photons wouldn't be any longer be able to factorize it in a particle physics term and a astrophysical term, because the particle physics term will also enter in the J-factor determination. And there was a nice work by Body and collaborators where they basically derived effective J-factors, which are velocity dependent, where they included, for example, the effects of the Sommerfeld. But I will just give you with that, and I think that's all I wanted to say.
Okay, thank you, Francesca. Thank you so much for this comprehensive overview and excellent lecture. Are there comments or questions for Francesca? We may get like a couple of them at least before closing, if any.
I just have a very quick question. It may just be very simple. In the previous slide before last, when we were looking at the velocity dependent cross-section, that equation, for the flux, I'm a bit confused about that differential at the beginning, because is it the same as the normal flux, like d phi by dE? I don't know why it's d squared.
Yes, because you're right, because I was writing, it's a typo.
A typo, okay, thank you.
I decided to integrate over the solid angle, but I forgot to remove the square. Thanks.
Okay, thanks.
I have a question. It's just a question comment, because I know that there exist a lot of WIMP models, starting from the fact that you can introduce dark matter in different representations of and or I mean, yeah, with different quantum numbers, it can be a scalar, fermion, vector, tensor, whatever. So my point is, your results, which looks, or some plots that you showed us, look very general in the WIMP, because you said like, or the title of your presentation was like with WIMPs. So at what point those results, for instance, with the mass in the x-axis for the WIMP, represent these general models that you can find in the literature of particle physics?
Yeah, I think, I mean, this is again a question how you recast the limits that are derived typically. So this equation here with this factor of 1/8p is typical for a Majorana fermion dark matter. So then whatever model you have for scalar or vector dark matter, as long as it can annihilate into final states like quark bosons and vectors, which is, I think, the case in most models, then we'll actually change. One is when you change the normalization factor. And so this will be very easy to recast any limit on those models if only the normalization factor is changed. For example, you can eventually recast for Dirac dark matter. You can just remove a factor of a 2 in your limits, and you can get the same limits. I mean, the limits for a Dirac dark matter particle. But then you have to always double check what is the spectrum that you would expect in the specific model. They think also for scalar and vector dark matter, also there you can be more model-based, so have the full, in a specific model, having the full DND that you would expect, and then you have to redo the analysis from scratch. Or you can assume some kind of contact type interaction where you only care about the final states. And then those DND are very general because are only standard model physics spectra. Only depends really on the central mass energy of the process. And this can also for scalar and vector dark matter as well.
And in principle, yeah, you showed some the spectral features of like you expect generally from particle physics models, like the box-shaped spectra, or what else?
Electroweak corrections and
Bremsstrahlung processes. In principle, if one found let's say an exotic model of particle physics, in principle you can find new spectral shape.
Yes.
That is possible. There's nothing that
as long as you build up a model that has a new spectral shape, which observationally, so once it is involved with the energy resolution of the instruments, look very different from anything that's been proposed so far, then perhaps you can design the search in an optimal way. So this was the case for the line, for example. I mean, historically, people were looking only for bump. Then at a certain point, Bergstrom and collaborators came up with the possibility of having light line signal. And observationally, this was interesting because it was something completely different, for which also the analysis pipeline is completely different, the way in which you set constraints and you look for lines. And this is, I mean, any features which is specific and has a phenomenology which is particular, you can try to have a look at it. And this will then be very much connected on data analysis, because how really you can exploit spectral features to enhance the sensitivity of your search is a question of developing the code and understanding how you can optimize the signal over noise ratio, basically.
Okay, thank you very much. Very nice presentation, by the way.
Thank you.
Yes, I agree. Okay, so I'm going to stop here the questions. I remind you guys that we will have Gather Town still this afternoon, and probably Francesca will take a look around. So just in case
Yes.
you're interested to continue this.
I will just disappear from 4 to 4:15, something like
Okay,
this. But,
no problem.
I
Just
should be there.
go around and let's see if any of the students wants to chat with you informally.
Yeah, fine. And don't hesitate to write me if you have questions.
Thank you, Francesca. Thank
You're
you
welcome.
once again.
Thank you. Bye.
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 Okay, so we're going to reconvene at 12:15. For those of you that were late this morning, I remind you that we're going to have the FermiPy hands-on session in Gather Town instead of the lecture on the action-like particles because Manuel Meyer cannot make it today due to personal reasons. Yes, so let's resume there at 12:15. Okay, in 15 minutes from now. In any case, I'm going to leave the Zoom room open just in case. But again, let's meet there in Gather Town directly, and we will have a 2 hours hands-on session on the FermiPy thing. Okay, led by Javier Coronado Blázquez. Okay, so see you in 15 minutes.